Okay, so up to this point, we've basically only dealt with functions of one variable. So we've looked at, through all of your math courses, functions that look like this, where we have one input variable x and an output variable y. But if we want to actually apply calculus or math in general to real-world situations, most real-world situations depend upon more than one variable. So we want to be able to expand functions of many variables. Now, for this course, we'll often just focus on two variables because those allow us to graph and have a geometric picture of things because those will be in 3 space. But in general, the ideas will apply to functions of more variables than just 2. So let's start with an example to see how this will work. So we're going to create a table here. So generally, when we're looking at weather temperatures, we have a regular temperature, but then we also have a temperature adjusted for wind chill. So if it's cold out and the wind's blowing hard, it's going to feel colder than the actual temperature. So this wind chill, the temperature adjusted for wind chill depends on the ambient temperature. So just the temperature you'd feel if there was no wind. Let's call this T, and the wind speed. Right? The harder the wind's blowing, the colder it's going to feel. So let's let Z be F, and it's going to depend upon T and W be the temperature adjusted for wind chill. Okay, and let's suppose that we have this following table that gives this. So let's say our temperatures are given as follows. And let's go ahead and divide this up. Okay, so up here, this is the temp. And this will be measured in degrees Fahrenheit, and this is the wind chill, or wind speed. And this is measured in miles per hour. So let's go ahead and fill some of these in. Okay, so there's our table of values here for our adjusted temperature. So let's answer a few questions using this table. So maybe give you a second to copy this down if you're taking notes. Okay, so let's suppose our ambient temperature is 15 degrees and our wind speed is 20 miles per hour. What is the temperature adjusted for wind chill? So this is asking what is F, whereas F of TW, so the temperature goes in and then the wind goes in. So we're asking for what is this? So to do this, we're going to go to the temperature part here, and we want the temperature to be 15 degrees, and we want the wind chill to be wind speed to be 20. So we notice this is our value here. So this value should be -2. Okay. So let's look at a couple of others here. Okay, so if we have the temperature is 35 degrees, what wind speed makes it feel like 24? Well, we go up here to our temperature is 35, and we go down and we see here is 24, so we want the wind speed to be 20 miles per hour. Let's try one more for this example. Okay, so we want the temperature to be 25 degrees. We want what wind speed makes it feel like 12 degrees Fahrenheit. So we want temperature 25, so we're going to go up to the column with the 25 in it. So this is our column for 25. And now we want the wind speed that makes it be 12 degrees. So we're looking for a 12 in this column. We see there isn't a 12 in this column. We have a 13 and we have an 11. So it should be somewhere between these. So it should be somewhere between 15 and 20. So we'll go ahead and estimate that to be 17.5. Okay, and that's how we would use our table here where we have two inputs instead of just one input like we've seen in the past. Okay, let's try another example with an actual formula now. Okay, so person's body mass index, which is shortened by BMI, this is a function of both their weight measured in kilograms and their height measured in meters, and the formula is given by the weight divided by the height squared. So let's use this to answer a few questions. Okay, so what is the body mass index of a person that's 1.72 meters tall that weighs 72 kilograms? So what we want is we're plugging in 72 for the weight and 1.72 for the height. So it should be 72 divided by 1.72 squared. And if you put this into a calculator, this comes out to be about 24.34. And then notice the units here are the weight over the height squared. So kilograms per meter squared is our units for BMI. Okay, so in this case, we know the output and one of the inputs. So the person is 1.58 meters tall, and they have a BMI of 23.2, and we want to know what the person's weight is. So we have B of WH is equal to W over H squared, and we know two of these three things, so we can fill in the 23.2 for the BMI. I don't know the weight. I know this is 1.58 squared. So we solve this for W, and we have 23.2 times 1.58 squared, and this is about 57.92 kilograms. So working with functions of more than one variable when we're just working with equations is very similar. We just have more inputs to plug into our function. So now let's go ahead and do a few graphs so we can see what these look like. So recall from the flipped class video, we're working in 3 dimensions now if we have some function z is equal to f of xy that we want to graph. If we have more than 2 variables, we can't graph it because we'd be in higher dimensions than 3. So generally, our axes look like this. It is important, you can choose your x and y to be wherever you want, but then the z is determined by the x and the y. So think of, once you label your x and y, put your right hand with your fingertips pointing down the x-axis. Now close your right hand towards the y-axis, and then whichever direction your thumb is pointing is the z-axis. So you're kind of putting your hand like this here, and then you close, as you close your fingers this direction, your thumb is going to point in this direction. So that's how we label our axes. Okay. And so let's do some graphs now. You already saw several graphs in the flipped class video, but let's just do a couple here as well. So if we want z is equal to 3, what does this mean? This means we want any x, y, z, but I want my z to be 3. So I want any points that satisfy x, y, comma 3. So that means my x and y can be absolutely anything, but the z is restricted to be a value of 3. So if we label these things, what this means then is we go up here to 3, and everything on our graph has to be at that height, but otherwise it can be anything. So it's just a plane like this. So it's basically the same as the xy plane, just shifted up by 3. Three units. Let's try another couple more examples here for pictures. Let's look at x squared plus y squared equals 4. Now if we're just graphing this in the x, there's no z in this, so there's no restriction on the z. So if we were to think about what would this look like just in the xy plane, this would just be a circle of radius 2. But now we're saying, okay, we want to graph this in 3 space, and there's no restriction on the z values. So that means we can think of taking this circle that's in the xy plane here of radius 2, and we can just extend it up because it's going to, every value of z is acceptable here. So if we think of the points that are on this, they look like x, y, so we can think of this z, but we restrict x squared plus y squared to be equal to 4. But notice our z can be anything at all. Let's try one more graph. You can also graph these functions. Sometimes it's easiest to graph these using computer software. So you can use Mathematica. I showed several examples of graphs with Mathematica in the Flip class video. That's probably one of the better ways to actually do these graphs, but some of them we can kind of figure out like we've done the other ones so far just by kind of graphing pieces of it or recognizing the equations. So for this one, if we recall the distance between the origin and the point, so if I take some point up here, say A, B, and C, you can think of dropping this down. So the distance from the origin would be the length of, you should use a different color here. So the distance of this line here, this is the distance from the origin, call that D. And we can see this height here, this height is my Z value, so this is C. And now if I think of projecting this down, this would be my Y values, this would be B, and this would be A. So now, if I look at this distance here, that's just part of the triangle in the planes. This is A, this is B, so this is square root of A squared plus B squared. Color's kind of horrible, so let's change that color. Make it orange again. And so now if I know that distance, now I have the other triangle, where now this is the D I'm interested in, this is C, and this is square root of A squared plus B squared. So now D squared is C squared plus square root of A squared plus B squared, which is C squared plus A squared plus B squared. So using that, when I look at this equation up here, this equation is telling me my distance here, 9, is D squared. So D is equal to 3. So these are all of the points that are distance 3 from the origin. So what that should look like is just a sphere of radius 3. So this distance out here is 3, 3, and each direction 3. So that graph relied on us knowing the distance formula in 3 dimensions, which we just showed how to get. Okay, let's try one more. Say z is equal to 5 minus x squared minus y squared. So for this one is one we'll get used to using, but one way we can kind of figure out how to graph this is to graph it in the different planes and kind of just interpolate between the two. So suppose I look at the plane where y is equal to 0. This will give me z is 5 minus x squared. So we know what that graph would look like just in the xz plane. That would just be a parabola that opens down like this. And it would start up here at 5. And similarly, if we took x is equal to 0, I get z as 5 minus y squared. So that would be a parabola opening like this. And if we fix any particular value of z, so say I take z is equal to 1, then I would have 1 is equal to 5 minus x squared minus y squared, which is the same thing as x squared plus y squared is equal to 4. So that would give me a circle up here. It's giving me problems with the pen. So I get a circle like this up here. So we can see all of these are going to be circles of various radius. So you can see this is kind of like a bowl facing downwards. So we did that just by taking some particular values here and graphing things we knew already in 2 dimensions and using those to kind of interpolate what our overall graph would look like. So as I mentioned, we can use Mathematica to graph functions, but it's not always the most useful way to represent the data to actually go all the way to 3 space. So contour plots, this is a way to display 3-dimensional data in 2 dimensions. So you've likely already seen this lots of times. So what you can think of here are topographic maps where you're looking at, say, a map of some area and then maybe they label the heights at the various spots so you can tell whether there's valleys or mountains or whatnot. But also weather maps, when you watch the weather, they'll often display the temperatures on contour plots. So let's see some examples to see what we're working with when we mean contour plots. So let's consider the function z is equal to 2 plus x squared plus y squared. Now notice that for this graph, we're always going to have z has to be bigger than or equal to 2, because x squared plus y squared has to be bigger than or equal to 0. And so now to visualize what this graph looks like, we could do the same process that we just did before, but let's draw some contours instead. So let's start with the smallest value z can be, which is 2. So that gives me this equation, which is the same equation as x squared plus y squared has to be equal to 0. And that only happens at the point 0, 0. And then we can look at some other values. If I look at 3, this is equivalent to x squared plus y squared equals 1. And then let's pick another. You just pick enough values to kind of fill your contour in. I'm just picking some convenient ones. So we see at these different values, we're getting a point and then some circles. So now how can I represent this data in just 2 dimensions here? So what I do is I draw the contours. So I had just that point, and then I had a circle of radius 1 and a circle of radius 2. Like this. This is 2, this is 1. And then what I do is I label the z values. This is when z is equal to 2. This is when z is equal to 3. This is when z is equal to 4. So I put that, so what we could say is, if I'm on my graph, my 3-dimensional graph, as long as I walk along this circle of radius 2, I would stay at a height of z is equal to 4. So just to illustrate, let's draw a picture of that actual graph in 3 space and kind of see what we're getting out of this. So our graph for this would look like a bowl opening upwards. So when we think of our contours then, we have this lowest point here, and that goes down to there. And then so this is at z is equal to 3. And then we say, okay, up here at z is equal to 4. That would give me my circle of radius 1 down here. And then if I go up to z is equal to 6, I'm somewhere up here, say. And that would give me my circle down here of radius 2. And so you see, we're kind of just projecting this. So this is z is equal to 4. This is z is equal to 6. So you see, we're just projecting these down into the xy plane to represent the data. So you'll see a lot of three-dimensional data is represented in this way in actual applications. So let's look at a couple of examples of how to read these contour plots for such data. Okay, so we're going to have a contour plot below that's going to show job satisfaction, and that's a function of two variables, the hourly wage and the safety of the workplace. And so we're going to match the jobs at points P, Q, and R with descriptions. So first, let's go ahead and draw our contour plot here. So this is our hourly wage. This is our safety. We're going to put numbers on these. The numbers aren't going to mean a whole lot for us in terms of what the safety mean, but we can put them on here. And so let's suppose our contours look something like this. Okay, now let's label our spots. Let's call this one P, this one Q, and this one R. Now let's give our descriptions of the different situations. Okay, so the first situation is the job is so unsafe that just increasing the pay would not increase job satisfaction. So for the second one, we trade a little bit of safety. So we're okay with making the job be a little less unsafe as long as you increase the pay. And the last one is the job pays so little that increasing safety doesn't help. Okay, so notice that all of these points are on the same contour line. So that means they all three of these points have the same job satisfaction. So for the first one, we're saying it's super unsafe. And so even though you've increased the pay, it stays the same satisfaction. So we want to go low on the safety scale, so low on the y-axis here, and high pay. So that's going to be this one. So we stayed the same job satisfaction, even though we increased the pay because the job is so unsafe. For the next one, we're allowed to go, we'll take a little less safety, but it's not going to change our job satisfaction as long as you increase the pay. So that one's going to be right here. That's going to be Q. Because we've dropped the safety a little bit, but we've upped the pay and we stayed at the same job satisfaction. And then the last one, it's so unsafe, even though it pays so little that even though it's super safe, it doesn't help. So that one's going to be P. It's super safe, but the pay is really low. So we're going to keep that as P. So that's how we read the contours on that one. So let's try one more example of how we can read information off of contour plots. Okay, so some manufacturer has two products that they're selling, one at a price of $3,000 a unit and the other at a price of $12,000 a unit. Okay, so the manufacturer sells Q1 of the first product and Q2 of the second product, and the total cost to the manufacturer is $4,000. Okay, so our first thing is going to be just express the profit as a function of Q1 and Q2. So for this one, we could say P is a function of Q1 and Q2. So we're going to bring in a revenue of 3,000 Q1 plus 12,000 Q2, and then we subtract the cost, which is 4,000. Okay, and so for part B, let's sketch curves of constant profit in the Q1, Q2 plane for, say, profit of 10,000, 20,000, and then let's do the break-even point of we don't make any money. So notice if P is 0, we'll start with the smallest one. So this would say 0 is equal to 3,000 Q1 plus 12,000 Q2 minus 4,000, which is the same as 4,000 is equal to 3,000 Q1 plus 12,000 Q2. And since we're going to graph this in the Q1, Q2 plane, and this is a line, let's go ahead and put it in a form we're familiar with. So this is going to be solved for Q2, so I'm going to get a 1/3, so the 4,000 divided by 12,000 minus 1/4 Q1. So that is the line that gives me a break-even point. If I do 10,000, do the same setup. So I'm going to have 10,000 equals 3,000 Q1 plus 12,000 Q2 minus 4,000. So if we go through and we solve this for Q2, we're going to get 7/6 minus 1/4 Q1. And finally, if we do 20,000 and do the same setup, skip the steps here, this is going to be 2 minus 1/4 Q1. So now we can graph these three lines in the Q1, Q2 plane. And so we'll start when we have the profit equals 0 here. Notice that when Q1 is equal to 0, we're at 1/3. And when Q2 is equal to 0, we're at 4/3. So those are my 2 points that the line is going through. I didn't need to do that. So it's going to be something like this. So this is up here at 1/3. This is at 4/3. And this is the value when P is equal to 0. So anywhere along that line, whatever we sell for Q1 and Q2 is going to give us a profit of 0. And we're going to go up a little bit. And so this is the line at 7/6 and 7 times 4 over 6. And this is when P is equal to 10,000. And then we go up a little bit more. This will be up here at 17/6. And this would be down here at 8. And this is when P is equal to 20,000. So any value we take along these lines, so any value, any of those dots there, whatever value of Q1 and Q2 give that, the profit would be 20,000. So as you move along these lines, that's telling us we're going to get the same profit anywhere along that line.